Hello, folks. Today, I would love to cover how you can write a smart contract purely in Yul. Okay, so what is Yul? Yul is a different language than Solidity, but they're very related in many ways. Okay, so I'll show you how to do it. I'll show you how to write Yul contract. I'll show you the syntax. I'll, teach you a little bit about how it works behind the scenes. And then also how to compile Yul code with Hardhat and how to deploy it and how to test it. So we're going to write a whole contract, a smart contract in pure Yul. All right, let's jump in. So here we have a folder. It's empty except one file, the example.solidity file. We're going to take a look at that file. And this is Solidity code. So you're probably familiar with this. We're going to pick the Solidity version via a pragma. And, we're just going to set that equal to 0817. We have our contract. We're going to give our contract a name. It's going to be called example. In that example contract, we're going to have one function called something. It's going to be external. It's going to be view because it does not modify state. And it's going to return a uint 256, or just a uint. Sometimes you'll see that used as well. In this contract, or in this function rather, I'm going to define a new variable. So it's just a local variable in the stack called uint, called a, and it's a uint 256. Okay. Now, this is something you may have seen before, but I'm going to open an assembly block. Okay. And we're going to set a value. We're going to set a to some value. So we're going to say a equals, and notice the colon. That's just the syntax of this assembly. A equals 4, and we're going to return a. So this is a perfectly valid function. Yeah, and again, you may have seen this. You can do all kinds of things inside of this assembly block, such as storing things in memory. Okay, so you can mstore in location 0 in memory. Memory is just an array. I covered that in another video. But inside location 0, index 0 of the memory, I want to store the value 2. Okay, and then do something with that. In this case, we're not using it for anything. But the point is just you can do things that you can't do in normal Solidity. This is like more closer to the metal, so to speak. In assembly, you can get access to whatever you want, storage, memory, in exactly the way you want it. Whereas Solidity overall is an expansion of Yul in a sense, and it has more, protections in place, so to speak, and more high-level tools. So I said Yul right there. That's because this assembly block is actually just Yul. So they didn't do this. They didn't call it Yul. But technically, when you open this assembly block, you're writing in Yul. So you have to write it like this. It's technically not assembly, but that's just what they called it, this block. But this inside this block is Yul. The question now is, could we actually have written this entire contract in Yul? Could we have done something like this? Assembly. I want this whole thing to be in the assembly block, to be Yul. Okay? This is not valid syntax, but I'm just saying that's what we're trying to do. Can we do this whole thing in Yul? Okay? The answer is yes. And we're going to do that today. Okay. So, all right. So let's get started. First of all, we're going to remove this Solidity file. This was just to give you an idea of, what Yul is and what we're talking about here. What we'll need to do is install Hardhat. Okay. So I do have some browsers up here, on my end, just to make sure that we get done everything smoothly. So we're going to yarn init, this folder. We're going to say yes to everything. Specify this to your own project, of course, what makes sense. We're going to say yarn add to the development dependencies, Hardhat. So this is how we even get started with Hardhat, how we install it. Okay. And then in the meantime as well, I'm just going to go fetch. There's a bunch of helper libraries that are good to install as well. This is also specified on the website, but I'll just install all these things as well. Where did I get all those things? Go here, right here in the Hardhat. You see this? Under creating a new Hardhat project, I'm following these instructions, and you can add these extra things at the bottom. And then as they say, you need to go in and add this as well to your hardhat.config file. Okay. So let's go into, we need to actually start Hardhat. Okay. And what we're going to do is just create an empty file. We'll change this, we'll modify this file. Okay. And what we're going to do is add the, this require statement inside this config file. Okay. So this is all specified on the website. Now I'm going to add just a few more packages on top of it. All right. So that's just installing Hardhat into a new folder. It is just modifying the config file to work with these extensions, and now it's installing the extensions. And I think that I had one extension too many here. Okay, so we'll give that a second. Okay, nope, we are getting some issues. So we'll just try to call this exact command right here. All right, so everything is done now. Hardhat is installed. The Hardhat config is ready. Like, we added that require statement. And then we also have all the so-called, like the helpers, the plugins here, if you will. All right. So now Hardhat is set up. We have a few files and folders in our folder now that was created for us. But as you can see, it's pretty bare metals. There's no contracts or anything, example contracts. You could get that by picking the JavaScript or the TypeScript version when we set up Hardhat in the first place. Regardless, we'll get started. So what we're going to do is we're going to create a contract folder, and we're going to go into that contract folder and create a contract called Pure Yul. And I will give it the .sol extension. It is going to be Pure Yul, but just for syntax highlighting, it's helpful to have a .sol. VS Code also supports the syntaxing if you do .sol, even though it's Pure Yul. But some of you might do .yul. That's fine. You just won't get the syntax highlighting unless you have a plugin that can handle that. So in here, it's actually very easy to write the Yul contract. It's very kind of like basic, raw, if you will. One thing we're going to do is we're going to give it a name. So we're going to say Pure Yul, and we're going to open this object code here. And then inside the object, we're going to create the constructor. Okay. So the outermost object, Pure Yul, that will be the one we compile. That object has a code block under it here. This is the constructor. Okay. We're going to write another area. An object can have sub-objects within it. And this object down here will be the actual runtime code. Yeah, let's just call it runtime. There are some benefits in naming it with a name _deployed for gas reasons, but I'm just going to call it runtime now because it makes it clear that's the runtime code. And that is an object that can also have a code block under it, which will be the actual runtime code. So what is actually being deployed, right? So remember with smart contracts, when you create a new smart contract and the miner picks up your transaction, okay, you're going to send it to basically address 0. Okay, so that's how you construct the transaction in the first place. I won't go into those details, but that's how it is. When that contract is created, the miner will pick up your transaction. It will take the code you sent along, and it'll execute the constructor part of the code. That's what we're seeing at the top here. Once the constructor part is executed, it will that constructor part is required to return the runtime code section of your transaction data, and it's the runtime part that will be put into the blockchain in the form of the code hash associated with the address of the contract. Okay, so the contract will be created by the miner. It will get an address assigned to it. It will be put at that location, and then the code hash segment of that location will be put the runtime code. Okay, so anyway, and then the point is the constructor is thrown away after that. You can never call the constructor again because it's not even stored in that contract. Cool. So what we're going to do here is actually just there's a special way to write this, which is basically we can basically say data copy. This is equivalent to code copy in the EVM, and we can get the data offset. Okay, we're going to get the data offset of runtime. What runtime? This down here. We can label all these objects, as you can see with the string literal runtime, and we can always refer back to them. So we can we're going to copy the code that sits at basically from 0 up to this data offset of runtime. Okay, and how much are we going to copy? Well, we're going to copy the entire size of the runtime code. So it's just a convenient way to quickly access that. And we're going to tell the caller, okay, that everything, so data copy again, it copies into memory starting at location 0. What does it copy? It copies the code starting at this data offset, right? So meaning starting down here with the size of runtime. Why starting down here? Well, we don't want to copy ourselves. We don't want to copy the constructor. Okay, so we need to first go to the offset of where runtime sits and then get the size of runtime. These are just helper functions that Yul has. So that's also why it's not pure like bytecode or anything. Obviously, we're writing right now. Yul is a language that has a little bit of helpers for us here. which is nice. And then we tell the caller, whoever called it, which would be the miner initially and eventually everybody, we tell the miner that, go look in memory starting at 0 all the way up to the size of the runtime code. Whatever that is going to be the code that you need to put into the code tree and like create the code hash and everything. So we can do other things in the constructor as well, but we should always end up with saying, where is the actual runtime code located? And this is what we're doing here. We don't need to do other things in the constructor for this example, but just so you know. Okay. Now I also want to show you just how to actually get the, syntax. You just go search Solidity Yul on Google or something, and it'll take you to the docs of Solidity. And under there, there's a Yul segment. So this is was previously called Julia, but now it's called Yul. And you can see they have simple examples. They do have full contract examples here, but I'll create an even simpler one today. They have all the syntax you can use. And by the way, this is also what you can use, of course, inside the assembly block in Solidity, but this is all valid Yul syntax. So there's no like greater than equal to sign like there is in Solidity. You have to actually use these functions, LT less than, and it describes what it does. So if you want to say is X less than Y, you just do LT, X comma Y. So it's a little bit, again, kind of bare metal. Anyway, what are we going to do in our runtime code? In our runtime code, we're going to have someone be able to call a function within our code here. Okay, so typically a smart contract, of course, has some functions you can interact with. That's the main purpose of these smart contracts, is that anyone can then call these functions. It'll check some access control and yada, yada, yada. We're just going to create a very simple function. Anyone can call it, and it just returns the value 4. That's all it is. Now, when someone calls this contract, they will call it with some call data. Okay. So if someone, Bob or someone or Alice calls this contract, they will send some call data along with it. And that call data, the first part of the call data, will specify which function in the smart contract they want to call. That's called the function selector. So what we need to do in Yul, and this is what all smart contract code does behind the scenes when it eventually gets compiled into bytecode, because this Yul will also be compiled into bytecode, is it has a switch function, like a switch function here, that on the selector, on the function selector coming in. So what do I mean? Switch is a Yul statement. It's just a normal, if you're familiar with other programming languages, just a normal switch. Like you switch on some variable, like some condition, and you're basically saying whatever that variable is, do one of these things that follow. So and then you follow it with case. So you're basically saying, let's say that this getSelector function, which we haven't defined yet. We haven't defined this yet, but this getSelector function returns something, and you're going to switch on that value, that return value. In case it equals 0x123, okay, do this, do whatever is in this block, do this. If whatever getSelector returned was equal to 0x123, do this. If not, keep looking in these cases. Was it equal to 2, 3, 4, 5? Then do this, and so on. Okay? So it's just a case statement that switches like that. In normal programming languages, it'll actually keep running through the cases, even though it found a match. In the Yul, this is not the case. Once it found a case, it runs that and it stops. And then there's also going to be a default in case, no pun intended, in case it doesn't actually find any of these function selectors. In case it doesn't find anything, we're just going to revert. We're going to revert, and we're going to say there's no return data message. Like we're not going to send that back any data when we revert. We're just going to revert the call, because in other words, we're not going to have a fallback function. Okay. So in other words, we're going to try to get the selector from the incoming call data. We will, based on what function the user wants to call, we will, call this code. And when I say based on what they want to call, well, we're going to define what the function is called. So let's go do that right now. We're going to go to jtk.eth online. We're going to define a function called myfunc. This is the function signature up top. This is the function selector I'm going to get now. 1, 2, 3, 4 bytes out of that jtk.eth of the signature. And then we're going to put that right here. Okay, there you go. So this right here is the signature of, or the selector of myfunc. Okay. So if someone calls this smart contract when we've deployed it with call data that includes this as the first part of it, The Yul code here will select this and it'll run whatever code is in here in my func. We are going to mstore in location 0, the value 4. So what this is we're going to go into the memory array, which again is just an array of 32 byte chunks, so word chunks. And we're going to store in the 0 index location of that array, so the very first slot of that memory array, we're going to store the value 4. So that's what this means. Store in location 0. Sometimes it's also denoted with a hex specifier, like in location 0x00, or you can just do 0. Store the value 4. Okay, once we've stored that, now that sits in the array, we can return data, and we'll return everything that sits in the first slot of memory, which is everything that sits in the first 32 bytes. 32 in hex is also 0x20. So in hex notation, there's 32 bytes. So we're going to just return the first word, because that's everything that sits between 0 and 32 bytes. And that's where we stored this for. So this will actually return 4, always. Okay, cool. So that's this. Now we need to actually write that selector. And what we can do is we can create like this kind of helper function down here. Okay. So we can do this, and we can do this, and we can say helpers. Okay, so we can do all these things with the comments to kind of help us. There is a function statement in Yul. You can actually create a function, and you can call it getSelector, which of course we have to because that's what we did above, and it can return a selector. That's how you do a return statement. You just do the arrow there and then selector. So we just need to define the selector in here. Notice again, the colon equals is how you set something equal to something else. To actually get the selector, I have pre-computed the function that does this, but let me tell you what this is. This gets the 0th kind of slot of the call data load, like it loads the 0th chunk essentially of the call data. Okay, so this will be like 32 bytes essentially of the call data. We only want the first 4 bytes of that. So one way to do that is to divide that entire chunk of data coming in. And notice that, again, the call data is certainly the function selector in the beginning, but it can also have all the kinds of parameters. We are not interested in them. We only want the first 4 bytes. The way to get that, or one way to get that, is to divide that by something that is 1 at that the first byte, like the least significant bit of this function selector. Okay, it has a 1 there and a 0 elsewhere, because that's like it handle integers here. So when you divide that out, it'll be something like this function selector dot something when you divide the two, and that dot something is going to get cut away. So this, in other words, is a long way of just saying cut away everything except the first 4 bytes. You can do this with other methods as well, such as bit shifting. But this is what they have in their online example. So this is just what it is. Get selector. Done. That is actually the code. We have our pure Yul code. Done. This has a constructor. It has runtime code, and all the runtime code does is handle a function called myfunc, and it just returns 4. So you can think of it as a kind of an external view function that just returns the integer 4. Okay, that's it. That's Yul code. Now what we're going to do is actually compile that. So I'm going to make a directory here, and I'm going to call it compile. Okay, inside compile, we're going to create a compile.js file. Okay, so now we'll get started with compiling it. All right. So what we're going to do is we're going to require, and again, so this is actually JavaScript now. Okay, so we're going to require, we're going to require path. We're going to need path. We're going to require, these are just the JavaScript packages that are nice. We're going to require these file system manipulation tools. We're going to require the compiler, the solc compiler. So you do have to install the solc compiler. Okay, solc is what compiles Solidity and also Yul. You can install it with brew, or you can install it with other methods. I think there's also Docker container that installs it for you. But if you just go online and say solc install, you'll figure out how to install that. We're going to define an output path where so what we're going to do now is in this compile.js file, we'll actually compile that Yul contract that I just created. And the contract will have a bytecode associated with it. That's what we're trying to get at here. And we're going to use the solc compiler to get that bytecode. Once we have the bytecode, we'll store it in a build folder. Okay. So every time we run this compile file, it'll just compile the Yul contract. So whenever we make some changes to it, it'll compile it and it'll put it in the build folder. So the output path will be the build folder. We haven't created that build folder yet, but that'll be the output path. Great. So we're going to path.resolve our current directory name, but remember that we're inside now the compile folder. You also see at the bottom, it says compile. And what we're going to do is go back to the root, and then we're going to go into a build folder that we have not created yet, but we will. And we're going to store this in something called pureyul.bytecode.json. That's where it will be stored eventually. That's the output path. Okay, we're also going to do an input path. Input path being where is the actual code located that we're going to compile. So that what we're going to need to load that, and we're going to need to send it into the Sol-C compiler. So what is the input path? Well, for here, we can also resolve dir name. Go back. This time we're going to go into the contract folder because that's where the Yul code lives. Again, we have the .sol extension, but it is still pure Yul code, as you just saw. We're going to actually read that file. So we're going to say read file sync. Okay. And we're going to do the input path to that. And we're going to read it in a UTF-8 encoding. Cool. So now we actually have the source data, the source code that we want to compile. We're going to define like a helper JSON. I'm just going to paste this in because that's much faster to do. I don't want you guys to wait. So this is the instructions for the compiler. Okay, for Sol-C, we're going to define a variable called input. It's going to be a JSON, and it's going to have the language specified as Yul. You can also specify this as Solidity, but this is not what we need to do now because then it would fail because the code we wrote is Yul. So the language is Yul. The sources is pure Yul.sol. Okay, so the content is right here, the source, because we actually just read that in here. So we can just directly say the content of this file is the source up here that we already loaded in, and that goes for this file. So you can imagine having multiple files you want to compile. You can define multiple sources. For the settings, we're going to say what do we actually want output from the compiler. We're just going to say we want the bytecode. It is not smart enough yet to give you the API, so you can't ask for that for Yul code at least. For Solidity code, you can. Okay, so that's the input to the Sol-C compiler. So what we're going to do now is call the Sol-C compiler. But before we do that, we just want to make sure that we're all good here. So I'm going to lock done to the console. And again, we're not compiling anything yet. And then we can call node compile.js. And then as you can see, this just said done. It says done here behind this recorder thing. Okay, so that works. But now we're going to actually compile it. So we're going to call Sol-C, and we're going to call the compile function on that. We're going to need to stringify this JSON file above. So what does that do? This command right here. It just turns that above JSON into a string. It just stringifies the JSON. So you can go from a JSON to a string and string to back to JSON. They look very similar, of course, because it just kind of recursively converts it to a string. But that's just because the Sol-C compiler expects a string as input. Done. That's it. That'll compile it. We're going to grab that compiled contract output. We're going to also get the bytecode from that compile. But, before we do that, let's just show how it looks, the compile contract. Let's take a look at it. So we're going to compile it again. And look at that. This is the compiled output. So the compiled output is also JSON, actually. It has a JSON that comes back. And in fact, it's a JSON string. Okay. So we're going to need to parse this into an actual JSON. But anyway, we can think of it as JSON. But anyway, so it has a contracts key. Under that, it has the file name that we compiled. So pureyul.sol. That was like that input section we wrote. And then pureyul is the contract name. And that has an EVM section. And under the EVM, we see the bytecode, under which we see the object. And this is the actual bytecode. Okay. These are actual EVM opcodes. You remember 60 is push, 53, basically specify like you're pushing a certain amount of bytes, and then push and so on. So you're pushing all these things. F3 is return. I believe FE is invalid. And then, so basically the constructor part is this. Okay. And the runtime code is this. Okay. So something like that. All right. So anyway, but the point is, this is the bytecode. So we're going to need to now actually get this bytecode out from this. So as you could see, we need to say something like this. Const, what's the actual bytecode? Well, we need to actually, first of all, parse this result as a JSON. So convert it from the string we just looked at. It kind of just looked like a condensed JSON, right? It wasn't that different. But anyway, parse that JSON string and then go under contracts. You remember there was a contracts field and there was a pure Yul.sol. And then we do pure Yul. This is just kind of from memory here. You see, go under the contracts. That's what we're doing here. Dot contracts. Then because this key has a dot in it, I can't just dot pure Yul.sol because it doesn't understand where the dot should be. So I have to put the brackets around and the quotes. But the point is that this is what this key is now. So I went under contracts under this, and now I'm going under pure Yul. Now I need to go under EVM and bytecode. So like this. So pure Yul dot EVM dot bytecode. And I'm going to also need to go under object. Okay, that's it. That's the bytecode. And we can actually console.log this bytecode. Okay. And let's try to run it. All right. There you go. That's the bytecode. So this is it has the deployment barcode, the init bytecode, which is the constructor right here, and then the runtime, which is the rest. Okay. Cool. So now we compiled it. Now we need to actually write it to the location. So we just compiled a pure Yul contract in Sol C. Now we're going to have to actually write it to the destination. So we're going to use the file path or the file system, and we're going to do the output path that we constructed earlier. We're going to actually have to convert that JSON back into a string. We're going to make sure it's stringified because remember that we parsed this JSON first, then went into this sub object called object. Now we're going to have to bring that back to JSON string for it to work. We're forced to create a fallback function. We can put nothing there. That's just how write file works. It does need this fallback function, but we can leave it empty. In general, you can catch any errors here. Okay, so now we're going to write to the output path, which again will be inside this build folder we haven't not created yet, and it's going to write this bytecode, and that's it. We're all done. Cool. I will run this one more time, but this will fail because we don't have the build folder. Okay. So it will complain. Okay, it did not complain. Well, all right, let's run it again. That's because we caught the error and we did not specify to tell us anything when there was an error. So always make sure it actually complains. All right, so here inside build pure Yul.bytecode.json, we have our bytecode. Great. So every time we call compile, it'll just put the bytecode right there. Next, what we should do is let's create the API. The API, again, the Sol C is not clever enough yet to give us the API of a pure Yul contract. So we're going to have to write that ourselves. But not to worry, we can do that. So pure Yul.api.json. What is an API? How do you write one from scratch? Let's do it. So the way an API works is it's really just a list. So we're going to open that list. And if there's no function in your contract, it's just an empty list. There's nothing. Okay? Like not even a constructor, nothing. Then it's just an empty list. If there is something, however, like a constructor and yada yada, then we need to write something. So in this case, we have a function. So the way you then define these things in the list is basically like a little JSONs here. Like each is a separate thing, like each function or event or like whatever it is you have in your contract. You have to write this mini JSON here. All right. So in here, we're going to do basically the name of the function, which is going to be myfunc. And it's going to take no inputs, but generally there will be an inputs field. It's going to be empty. And it's going to give us some outputs. And yeah, so, all right. And then the outputs will be, this is a little bit of syntax. All right. There will be an internal name of the outputs. That's just how that works. UN256. We'll also have a name. Oops, a name. We won't really call it anything. Like the return variable won't have a name. We're just storing for in memory and just returning it. Sorry, internal type. That's what I meant up here. Internal type, of course, is uint, and then the type is uint. All right, cool. So that's how you write these variables. You need an internal type, a type, and then a name for each of the variables. In this case, there's no name, and so on. Same format for the inputs, but we're also not taking any inputs for the myfunc. Okay? So that's generally how that is. All right? So we're also going to specify the type out here. So we're going to do type function. We're going to specify it's a function, and we're going to do state mutability. which just means like what can it mutate state, or like what is its state mutability type? Well, this is a view, so it cannot mutate state. Okay, cool. All right, so that's it. That's the ABI. That's how an ABI looks. Now, again, normally if you were to write that contract in Solidity, the ABI would come out of the Sol compiler as well, so you wouldn't have to worry about it. In fact, Hardhat would compile everything for you. You don't have to manually compile anything. But anyway, this is how you have to do it when it's a Yul contract. You have to tell it what the ABI is. Great. Now we have those two things. So we can compile, and let's do that again, just to confirm everything is fine. We compiled it. Yes, and we can build it. Fantastic. And we have the ABI. Cool. Let's do a deploy. Let's actually try to deploy this pure Yul contract onto the blockchain. Okay. And again, of course, this will be like our local blockchain here, but technically you would do it on an actual blockchain. Cool. So let's try to deploy it. So for that, we're going to use the Hardhat environment. So we're going to import Hardhat, and we're going to create an asynchronous function called main. And this main function is going to do things, aka the deployment, and we're going to call it the bottom there. So how do we define what it does? Well, we're going to fetch the API, or the ABI rather, and the ABI is going to be in the built folder under pureyul.abi.json. Okay, and then we're also going to fetch the bytecode, and we're going to require that from the same location. You could generalize this in a helper function. You could imagine even like importing a compile, like the compile file we had earlier, and kind of just like import the function that does the compilation and returns the ABI bytecode as return parameters. But for now, just because for no particular reason, we're just going to do it like this. Pure Yul contract is await hre.getContractFactory. So you've seen that before, get contract factory. Normally, you can pretty much just put your contract name here, right? Normally if it's a Solidity contract, you do something like that, and Hardhat takes care of everything for you. We cannot do that in this case. What we need to do is give it the ABI and give it the bytecode, and the syntax is ABI first. So we need to do ABI and bytecode like that. Okay. So this is now we're telling it, hey, we're showing up with the ABI. We wrote that ourselves. We're showing up with the bytecode. We did the compilation ourselves. Please just create a contract that with this ABI and this bytecode is this contract. So, and now we're going to say const pure Yul instance. Okay, so this will be the actual deployed instance. We're going to wait pure Yul contract dot deploy. So now we're actually deploying it. And then we're just going to wait for that to be mined and ready. So we're going to say pure Yul instance. So we're just going to wait that actually gets deployed by the miner and the network. And then we're going to console.log. It's typical that you just say, hey, the pure Yul contract was deployed to, and we can put the address of the pure Yul instance right here. There you go. That's pretty standard as well. All right, let's try it. So node deploy. The syntax is we need the Hardhat environment, and then we need to go under the Ethers plugin. And that's it. We just deployed a pure Yul contract to the blockchain. Pure Yul contract was deployed to this address right here. So again, this is the local Hardhat blockchain. We could also do Ganache if we wanted to keep it local, or actually do it to a real blockchain, but that would be an easy change. So this is how you deploy it. Done. In general, this is how you deploy any contract with just the ABI and the bytecode. Okay, what do we need? What do we need to do now? I want to show you how to actually test our Yul code. That's important. So what we can do is pure Yul.test.js. Okay, so we're going to create a test folder. Under that test folder, we're going to create a new test. So we're going to say, we're going to import expect from the chai library. The chai library is a fantastic JavaScript library here to test your functions. Like you can do expect statements. You're expecting something to equal something else and so on. It's a fantastic test library, something highly recommended. And what we're going to do is when we create these tests in general, if you haven't done that before, but it's just to create these describe blocks. So we're going to say describe for the pure Yul contract. Okay, we're going to create a sub function here under that. So we have this describe block, and we're going to say describe We're going to create another describe block so you can do these sub describes. The deployment, and this is just super helpful to kind of bundle together functionality. So anything related to the deployment will go under this describe. The outermost describe has everything, the entire test for this. But you could imagine that you could test other functions as well. So you could have other high-level describes. Anyway, for the deployment, now we'll get specific. So we say it. So that's like describe the deployment, and then it should deploy correctly. Okay, that is deploy correctly, like that. It should deploy correctly. Okay, and then the way to do the it statements is you can do an async function like that, and that's it. All right, cool. So it should deploy it correctly. Now, all right, we need to actually deploy it. To do that, we need to use the same code we just did. So we can go under deploy, and remember we have this under here. This will actually be the same. Oops. This will actually be the same. So I just copied that from there. We can move that in. Okay, so I just copied that over there. We need to move this in. We need to move this back. All right, cool. So I just copied that. Again, that's why it would probably be better to have this sort of kind of utils file that you can just import this bytecode and API from. But again, we're not doing that right now. All right, so now we've actually deployed it. So now we're just going to do our test, which is await. Expect that the pure Yul instance is, and then there's something called proper address. That's pretty cool. And we're going to duplicate that. Okay. And we're going to say is not null. Okay. So we're just making sure that the address actually is something, it's proper, it's not null, it actually gets deployed correctly. Let's try to actually test this. Okay. So the way to test this is to say npx hard hat test. And if this, okay, this is going to give an error if I call this, and I'll show you what the error is. So, first of all, we're going to need to say npx hard hat run test. All right. This is going to give us an error. And why is that? Well, because hard hat is going to try to compile the Yul file. Okay. And hard hat doesn't know how to compile the Yul file. So basically it's going to say, hey, under constructs pure Yul, there's this string literal. This does not look like a Solidity contract, and it errors out. So since we already compiled it manually, we can just tell hard hat to not compile it. Okay. And now it actually runs. We just have another issue in the, in our test here. Okay. And, another one. So hold on. So we need describe. All right. So this is not define the describe. All right. Okay. So we just need to call npx hard hat test and then the file, not the run command, by the way. Okay. So here we see that the test is actually running now, but there are some issues with the actual deployment. So we'll just go and take a look at that. Yeah. So what we're going to do is actually we need to get the actual address here out of that contract. All right. So now we can run it, and that's it. So it's passing. So that's it. We're actually testing our Yul contract. Now let's actually though test the function, of course. So before we do that, it is super helpful to just have a before each. So what we're going to do here is say pure Yul instance. We're going to define that up here, and we're going to create a before each block, which is highly recommended to do because this will actually make sure to reset everything that you do, like reset everything before each test. And what we're going to do is basically move the deployment up here. So for each test that runs, it kind of redeploys things, and that just makes sure that yeah, everything is nice and deployed. All right, so cool. So let's move that up there, and now that is deployed, and we're going to remove this, and then basically we're just going to have this state variable or this overall variable here that this makes us able to reference this pure Yul instance. But notice that we moved everything under this before each block. This is run before each test, and it'll give us available a newly deployed pure Yul instance. And then we can start acting against that. So let's just try this change. Everything still works. So the next thing we're going to do is describe the functions should work as expected, right? And we're going to do a function here. And under that, we're still going to do this it. It should run my func. Great. And we're going to create an async function again. And that's it. And so now we're actually going to call that function. And remember that the API specified that this function was available. So hardhat knows that. And we're going to take that pure Yul instance and we're going to call myfunc on that instance. Okay, so again, this is the myfunc that is in that pure Yul contract in the form of a function selector, right? Remember that the pure Yul contract, if we just open up contracts again, just to have it side by side, the top window now shows you the contract. The bottom window is the test. So the top window here, it doesn't have any function in here called myfunc. But through the selector that we get, and then through kind of casing through that, so to speak, we're going to switch on that, and then we're going to pick the selector of myfunc. And hardhat knows how to put that call together. So hardhat knows how to turn this into essentially this function selector. So by the time we make this call to this function and it gets into this part of the Yul contract, the call data already has this function selector in it. So there's nothing that we need to worry about. And then the switch statement will pick this function and actually call this and return 4. So that's a little wild, but that's how it works. And we expect this to equal 4. I'll start by saying equal to 2 just to make sure that this fails. But I like to do that in the beginning. Sometimes it can silently succeed in some cases. Notice now so we expect it to fail, that's good. But notice now that in our test, I'll call it again. I'd like to just kind of show you how all these describes and the it statements come out. We did the describe that says, for the pure contract, the deployment should deploy correctly. So notice we can read these tests in English, right? Like kind of in a flowing state here. That's why I like to name the describes and the it statements this way. So you can say, for the pure contract, the deployment should deploy correctly. For the pure contract, the function should work as expected. And then it should run myfunc. And, maybe this needs a little renaming, but that's the point. Now it says here, what was the actual? It was 4 that came out. What was the expected? We expected 2. That's because I wrote the test like that to fail. I like that to just see that it failed. Now, there is, of course, a way to say to not equal. Okay, so there's a way to say that. But I also just wanted to test that. So anyway, so now we expect everything to pass. There you go. We have 2 passes. So now we actually called the myfunc in the actual Yul contract. We tested that it worked and returned 4. And that's it. That's how you do a pure Yul contract. We compiled it. We wrote it, we compiled it, we deployed it, we tested it, we did everything in hardhat. I'm sure you can do the same thing in Foundry. So, and other frameworks, Truffle and stuff, but we just did hardhat. But anyway, so yeah, I'm really happy that you watched. Feel free to subscribe and like for more content like this. Let me know what worked, what did not work so well. And I'm happy to adjust and to basically do a video on any content you'd like. Maybe we dive a little bit more into the function selectors if you want, like how it actually works behind the scenes. Whatever you'd like to see, just let me know in the comments section below. And thanks for watching.